Life on the razor's edge, why living systems thrive between order and chaos. 1. What exactly is the edge of chaos? Imagine a thermostat dial with frozen solid order on the left and utter bedlam on the right. The edge of chaos is the narrow sweet spot in the middle where small tweaks still matter and rich patterns emerge. Chris Langton first put formal numbers on that idea while studying cellular automata in the late 1980s, showing that computation, signaling, and novelty peak right at the critical borderline. Stuart Kaufman later argued that life itself settles into this zone because it balances reliability with the freedom to innovate. 2. Why living systems prefer the edge. 3. How did life get there? 1. Self-organized criticality. Per Bach's sandpile metaphor showed that some systems naturally tip themselves to a critical slope where avalanches of all sizes are possible. Organisms may be no different. 2. Natural selection's feedback loop. Species that were too rigid died out in changing climates, while those that were too chaotic lost useful memory. Over deep time, selection nudged biochemistry, brains, and ecosystems toward the razor's edge where adaptability and stability coexist. 3. Network constraints. Gene regulatory, neural, and ecological webs have connection densities that statistically drift toward critical thresholds. Evolution can only play with the wiring it inherits, as Kaufman puts it. 4. Landmark writings and big-name thinkers. 5. Today's evidence, and the pushback. Proof piling up. Brains on the brink. Neurons fire in avalanches whose sizes follow power laws, a hallmark of criticality. Microbes in the lab. Protist populations flip between ordered and chaotic growth, hugging the critical line under nutrient stress. Healthy skepticism. A 2023 survey of 72 cell process models found many far more ordered than edge of chaos theory predicts, hinting that robustness may dominate at the molecular scale. Some physicists note that multiple critical regimes exist, avalanche versus edge of chaos versus percolation, so claiming a universal principle may be premature. 6. Open questions worth watching. 1. Scaling. Does criticality cascade smoothly from proteins to brains to ecosystems, or does each layer tune itself differently? 2. Computation limits. Can artificial neural nets gain new tricks by steering themselves to the edge, as recent machine learning papers suggest? 3. Therapy and design. Could nudging tumors, immune systems, or synthetic biocircuits away from criticality make them safer or more controllable? 7. Quick read takeaways. Edge of chaos equals maximum adaptability. Too much order freezes change. Too much chaos erases memory. Life self-tunes through evolutionary feedback and network constraints, no external dial required. The evidence is mixed but growing, from sandpile math to firing patterns in your cortex. Debate continues, and that's healthy science in action. Bottom line. Whether you picture a sandpile about to slide, a neuron network crackling with balanced sparks, or an ecosystem poised between bloom and bust, the edge of chaos remains one of the most alluring ideas in complexity science. It explains why living systems are just stable enough to keep it together and just unpredictable enough to keep evolving, and why our own research, like life itself, is most exciting when it's walking that narrow ridge.